Okay, picture this. You're watching a car drive down a street. It starts up, it speeds up, it cruises for a bit, then slows to a stop. Simple enough to say, but what if you wanted to tell its entire story? I mean, every single change in speed, every moment of acceleration, with total precision. Well, that's exactly what we're going to break down right here. Because, just saying something is moving, that's only the first sentence of the story, right? Is it going fast? Slow? Is its speed steady, or is it all over the place? To really get what's going on with motion, we need a language that can capture all those little details. So let's dive in. We're going to start with the simplest trip you can imagine. A car that's just cruising along at a perfectly constant speed. No speeding up, no hitting the brakes, just a smooth, steady ride. This really simple idea is actually the key to unlocking everything else. Now, to tell this car's story, we're going to look at it in 3 different but connected ways. You can think of them as 3 different languages, all describing the exact same thing: a visual diagram, a data table, and then a graph. First up, the visual story. So imagine our car is dripping a little drop of oil onto the road every 5 seconds. Since it's moving at a steady speed, those oil drops are going to be perfectly evenly spaced. It's the most intuitive way to see constant velocity. It's covering the exact same ground in every tick of the clock. Okay, now let's turn that picture into some hard numbers with a data table. So at time 0, we're at position 0. Makes sense? After 5 seconds, we're 10 meters down the road. After 10 seconds, we're at 20 meters. You see the pattern here, right? For every 5 seconds that pass, the car moves another 10 meters. This table is telling the exact same story as the oil drops, just way more precisely. And last but not least, the graph story. This is where the magic happens. If we take those numbers from our table and plot them, with time along the bottom and position up the side, something really cool happens. All those points line up perfectly to form a straight line. And this is a huge rule to remember. Constant velocity always gives you a straight line position time graph. But here's where it gets really interesting. That simple straight line is holding a secret. It's not just a picture of our data. It actually has a precise physical meaning hidden right there in its shape. Now, before we reveal the secret, let's just do a quick calculation of the car's velocity. We know it travels 10 meters in 5 seconds. So displacement divided by time, that gives us a velocity of 2 meters per second. Just hang on to that number for a second. 2 meters per second. All right, let's talk about slope. You probably remember this from math class. Slope is just how steep a line is. You figure it out by taking the vertical change, the rise, and dividing it by the horizontal change, the run. For our graph, the rise is the change in position, which was 10 meters, and the run is the change in time, which was 5 seconds. So here it is, the big reveal. If you calculate the slope of our line, that's rise over run, or 10 meters divided by 5 seconds, what do you get? You get 2 meters per second. That's the exact same number we got for the car's velocity. And that's no coincidence. On a position time graph, the mathematical slope is the physical velocity. They're the same thing. And this is why graphs are so incredibly useful. Once you know this one rule, you can compare how fast things are going just by looking. See a line with a gentle, shallow slope? That's a slow-moving object. See a line that's super steep? Well, that thing is moving way faster. The steepness tells you the speed at a glance. Okay, so we've totally nailed constant velocity. But let's be real, most journeys aren't that simple. What about a more interesting story? What happens when our car's actually speeding up? How does that change our graph? Check out the data for an accelerating car. Look closely here. In the first 5 seconds, it only goes 1 meter. But in the next 5 seconds, it travels 3 meters, then 5 meters, then 7. See that? It's covering more and more ground in each time slot. It's definitely speeding up. So, here's the question for you. If a straight line means a constant speed, what kind of shape do you think this new data for an accelerating car is going to make on our graph? Boom, it makes a curve. It's not a straight line anymore because the velocity isn't constant anymore. The line starts off kind of shallow, and then it bends upwards, getting steeper and steeper as it goes. And here's the beautiful part. That rule we learned about slope, it still works perfectly. Look at how the line is getting steeper. That just means its slope is increasing. And since the slope is the velocity, an increasing slope means an increasing velocity. The curve itself is telling you the car is accelerating. So, what would the opposite look like? What's the story of a car that's slowing down or decelerating? Well, its graph would look something like this. It starts off really steep, and then the curve starts to level off or flatten out over time.
A steep slope at the beginning tells us it was going fast. But as that line gets less steep, as it flattens out, its slope is decreasing. And a decreasing slope just means a decreasing velocity. The shape of this flattening curve is literally the visual signature of an object hitting the brakes.
So there you have it. In just a couple of minutes, we've basically learned how to read the visual language of motion. Let's just do a super quick recap of the grammar, the basic rules of these graphs. It really is this simple. You see a straight line, that's constant velocity. You see a curve bending up, getting steeper, that's speeding up or accelerating. See a curve that's flattening out, that's slowing down, decelerating. And no matter what, the steepness of the line at any point tells you exactly how fast it's going right then. What's so amazing about this is that a line on a graph is so much more than just a bunch of data points. It's a narrative. It's the complete second-by-second story of an object's journey through space and time, all captured in one single elegant shape. And that kind of leaves us with one last big idea. We've used these graphs to understand a car's motion, but this language applies to, well, everything. From the stock market to how populations grow, graphs are telling stories. So the real question is, what other incredible stories can we uncover just by learning how to read the shape of a line?